Good morning, Science 9 students. Welcome to your first distance learning lesson. Today we're looking at electron arrangements in the periodic table. So I've got a couple things to cover. Some of it you may be seen before, kind of, but some of it will be new to you. So we're going to get started. First of all, I'd like you to go back to, hopefully you're on the internet just now, to go to YouTube, maybe pause the video just now and go to YouTube, have that open as a window, and also bring out your sheet that I gave you before the break that had Bohr diagrams on it for the first 3 rows of the periodic table, and on the other side of the sheet there was a periodic table, so please bring that out. Okay, so now that you have that out, I'd like to just go through a couple of topics here from that. Again, you'll probably have this written down already on the sheet, but I'd just like to run through it for the first 2 rows of the periodic table. So this is row 1 right here. We have hydrogen, very simple. It's got 1 proton, no neutrons, and 1 electron as an atom. Helium's got 2 protons and 2 neutrons. Now, there are other versions of these atoms that have more neutrons, but any atom for any element has a certain number of protons that is only ever found in that atom. For hydrogen, it's 1. For helium, it's 2. Going down to the second row, we see that we're starting to fill another valence shell. Notice, shell 2 got filled. We have to start filling, shell 1 got filled. We have to start filling shell 2. In lithium, we only need to place 1 electron there. Beryllium, we're placing 2. Boron's got 3 in there. Carbon's got 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And neon, should have written that down. The noble gas neon here has 8 in its outer shell, 10 in total. Remember, you fill the first shell with 2 electrons. After that, you have to start filling the second shell. Once that's filled, once that valence shell is full, you're filling the third shell. Something else I have not noticed to you is this, mentioned to you is this. See what I have written here across the bottom. Atoms get smaller as you go from left to right. Now, that only applies for within the row. That's a bit counterintuitive. You might think more protons, more neutrons, the atom's going to be bigger. Why do the atoms get smaller? Well, it's like this. For lithium, we've got 3 protons, 4 neutrons, and we go across all the way here to neon that's got 10 protons. Now, I would recommend you watch a video. It's a TED Ed video called How Small is an Atom? Try watch that on YouTube as well. What that video shows you is just not only how small are atoms, but how small are the parts of the atoms. Specifically, how small is the nucleus relative to the electrons. And what you find is that the electrons fill, although they're very small and they have tiny mass, in comparison with the protons, they fill a huge amount of the space. Most of the atom, at least as described in the video, is empty space. So how does that connect with the size of the atom? Well, the deal is this. You know how we said in the electricity unit that opposites attract. Well, protons and electrons are opposite in the way that their electrical charges. Electrons have a negative charge. Protons have a positive charge. They're naturally attracted to each other. Because they're attracted to each other, the more of the protons that there are, the stronger that attraction is. And so the atoms are progressively smaller as you go from left to right because there's more protons in the nucleus to suck those electrons in. Now, when you drop down to the next row, say from period 2 down to period 3, then all of a sudden you now have another shell to deal with. So the atoms get bigger again, and as you go from left to right within that period, the atoms are smaller because the nucleus with those protons is sucking those electrons in with greater strength. That's what I wanted you to know from the electron arrangements in the periodic table that I hadn't already told you when we looked at that sheet on board diagrams. Again, I do recommend that you look at your notes for the day here. Here they are, by the way. Lesson 5, what you should be working with. That you look for the notes for the day, and at the top, you do have assigned viewing. I recommend you do that assigned viewing as well as watching my video just now. That's on Tyler DeWitt YouTube channel, and also there's reading on page 66. The other thing that's totally separate I want to show you about is this here. At the bottom, the notes I'm about to show you are at the top right of the board here. We're looking at chemical reactions. This is an example of a classic chemical reaction between sodium and chlorine. I recommend you look for a YouTube video on it. It's not hard to find them. So here, there, that's what I meant to do. On this side of this, what's called a reaction equation, we have an atom of sodium, written right here, and an atom of chlorine. Oh, by the way, how do I know that they're that? Well, an atom of sodium is the only kind of atom that has 11 protons. It has 12 neutrons. Atoms of chlorine are the only kind that have 17 protons. Most of them have 19 neutrons. Also, there's a lot to unpack here. I filled the electron shells just like you're supposed to. 2 in the first shell, 8 in the second shell. Now, we don't have 8 in the third shell because this is just sodium. All we need to do is to put in 11 to make the atom. So it's got that one lone electron in that outer shell. Sodium is very reactive because sometimes we say it wants to get rid of that outer electron. What's really happening is that electron's really far away from the nucleus of the atom. The sodium atom is only got a very loose hold on that electron in comparison with this atom right here of chlorine. Count the valence electrons. Count the outer shell electrons. It's got 1, 2, 3, 4, 5, 6, 7 of them. Notice what I'm focusing on right here. Empty. That's an empty spot. There's no electron right there. We're stopping at 7. A full shell is 8. This one's only got 7. The chlorine atom, a halogen, only has 7 valence electrons. But what's happening here in this chemical reaction is we've got electrons being transferred, as you see in the title for what I wrote up there at the top. Electrons are being transferred in this chemical reaction. The arrow here just means makes, creates. This is what happens. It produces. What does it produce? Well, an electron is going to be transferred from the sodium to the chlorine. We're going to make a kind of a compound called an ionic compound. Again, watch this one on YouTube, sodium and chlorine chemical reaction. Using board diagrams, here's how we describe what's going on. There is a lot to unpack here, I know. First of all, this is something you haven't seen before, the square brackets. The square brackets, that says we're dealing with ions. So when you see square brackets like that, it means that what's inside there has a different number of protons as it does electrons. It could be more electrons than protons, or it could be more protons than electrons, or it could be fewer protons than electrons. Either way, it's got an electrical charge because there's a difference in the number. If the numbers were equal, the negatives being equal to the positives, then there would be no electrical charge. But as soon as you got an extra electron in comparison with the proton, you've got a negative charge. As soon as you have an extra, as soon as you've lost an electron, you have a positive charge. Hey, by the way, a key thing here is that the protons never get moved around. It's only ever the electrons. Chemical reactions involve electrons being transferred or electrons being shared. The protons don't get messed with. It's very difficult to break up an atomic nucleus. That doesn't happen in a chemical reaction. What has happened here is that valence electron from sodium, that outer shell electron from sodium, got transferred. Chlorine has a greater ability to pull in those electrons. It's got 7 valence electrons, a nucleus that's powerfully pulling in more electrons, and we say, air quotes here, wants to fill that last spot, that last position in its valence shell. Here's what else to look at right here. I want to notice the top right by the sodium ion. Here it says sodium ion. Symbol there has got a little plus. That means the sodium has a positive charge. It has a positive charge because it lost an electron. And chemical reactions are about the transfer of electrons. The chloride ion has got a negative charge. Oh, by the way, I didn't say chlorine ion. Some of you have probably heard already about the compound the chemical we call sodium chloride. That's this stuff right here. An electron has been transferred in this chemical reaction from sodium to chlorine. We don't say we have a chlorine ion. When it becomes an ion, when it gets that extra electron, it becomes what we call chloride. And it has that negative electrical charge. You're more familiar with this as simple table salt. You have this on your food. The white crystals that you put on your scrambled eggs or whatever are sodium chloride. They're made of sodium ions and chloride ions. Something I'd like you to notice as well is there's a connection here with noble gases. You know that neon is the noble gas that we find in the bulbs that light up the science lab. You know that those little Christmas lights, you probably are aware, like these days they're mostly LEDs, but when I was a kid, there were always those incandescent light bulbs. You know, I think, that inside those incandescent light bulbs is a noble gas called argon. This is interesting because the sodium ion has got 10 electrons in total, 8 valence electrons. This is the same electron arrangement as neon. Chlorine, now that it's an ion, chloride ion, has 18 electrons because it got that extra electron. If you look in the periodic table for the element that's got 18 protons and 18 electrons, you're going to find that's the noble gas argon. Now, you might ask yourself, well, why doesn't this just vanish? Why haven't we made just more noble gases? The answer comes down to the fact that these are not atoms, these are ions. They have electrical charges, and so they're naturally attracted to each other to form the cubic crystals that we call table salt. So that's an example of an electron transfer in creating a chemical compound. I thought just for fun, I'd show you a couple of examples of making ions, chemical reactions making ions. So, striker. There. What I've got here is a container here that's got iron filings in it. Elemental iron. Element 26, you'll find it in your periodic table. These are atoms of iron that I have in little crystals of iron. Let's see how this shows up. Not bad. I'm going to turn off the lights. Now, if I feel around here on the surface of the table, I can feel some grit. Some of that grit is just iron filings that didn't burn, but it's a little bit brownish. When you see a color change, that's kind of a hint that you've made a different chemical element. A different chemical. We got the same chemical element, but we've made a different substance. In this case, we've taken iron and we've made a compound called iron oxide. You'll know that better as rust. The next reaction I thought I would show you involves a more reactive element. That is this stuff right here, calcium. You may remember from your periodic table, your Bohr diagram, that calcium is in the third row. You might also remember that it's a kind of an element called an alkaline earth metal. So it's right next to potassium. I do suggest you look at a YouTube video throwing potassium in water. That's pretty dramatic. But even adding calcium to water gives you a fairly dramatic reaction, or at least a reaction that's kind of cool to watch. Or maybe not, I don't know. Let's see. This is elemental calcium right here. Something I'd like you to notice about it is that it's kind of white. It's not been stored in perfect conditions. The white color is not calcium. The white color is actually calcium oxide. I wouldn't want to handle this if I had wet hands, because the calcium oxide would dissolve into the water. It would make lime water, and that would eat away at the protein that is my skin, which would be bad. If we put it in water, oh, good, it worked. There you are. So there we have a chemical reaction. What's happening is you're making a compound called calcium hydroxide. You don't need to worry about that. Other than to say this, the calcium is involved in a chemical reaction. If you look in period 3 for the periodic table, you'll realize that calcium has got 2 valent electrons. Calcium doesn't like to share valent electrons. It would just as soon get rid of them. It does not have a strong pull on those outer shell electrons, on those valent electrons. Instead of just sharing them like some elements do or some atoms do, it gives them away. In fact, it's so reactive that it's giving them away to the water. Oh, this is actually getting pretty cool. My bad, not wearing glasses. So you can't feel this, of course, but you know the evidence in front of you is obvious. It's a powerful chemical reaction. Calcium very readily gives up its 2 valent electrons in a reaction with water. We wouldn't normally think of water as a very reactive substance. Here it is. The reaction's done. I feel the beaker, and it's noticeably warmer. There's been an increase in temperature. All of this is evidence that we've had a chemical reaction happen. Release of gas, change in color. And if you go to the periodic table, it makes sense. Calcium has got just 2 valent electrons. There's not a whole lot to give up to make it have the same, to make it lose those 2 valent electrons and form a different substance. Hey, by the way, if you look in the periodic table, you'll notice Calcium's got 20 protons. An atom of calcium, like the chunk of metal I showed you earlier, has got 20 electrons. 2 valence electrons only. It's in the second column. It's got 2 valence electrons. When it gives those up, it has 18 electrons, just like argon. This calcium here, these atoms of calcium, have got that noble gas stability that I talked about. It's not reacting anymore. I made a reactive substance, but it's not as reactive as the calcium atoms were themselves. I don't have any assignment for this lesson other than to say I'm looking for you to write down here, and write down in your notes here what I wrote down on the board over here. The next assignment I do have for you is a lab activity. We'll get to that soon.